It looks like nothing. Just a tiny metallic sphere, smaller than a grain of rice, tucked away in ancient rock. At first glance, you'd probably think it's some kind of natural mineral, or maybe a contaminant from modern times. That's what scientists thought too, until they dated the surrounding rock, 65 million years old. Long before humans, long before cities, tools, or even primates. And here's where it gets strange. The sphere isn't just metal. It's fused, in a way that mirrors the byproducts of nuclear explosions. Not naturally formed, not volcanic. We're talking industrial heat, precision alloying, like something you'd find at the bottom of a bomb test site. But that makes no sense, because nothing that should have been capable of making this existed when this thing was formed, unless we're not the first. Okay, let's entertain this for a second. Let's say those strange metal spheres and radioactive traces aren't just random geological flukes. Let's say they're real, and they point to something deliberate, something intelligent. Because if the Silurian hypothesis is even partly true, if advanced civilizations existed on Earth before us, then everything we've built our understanding of history on, it's wrong. That neat timeline where we start in caves and end up with smartphones, it's not a ladder, it's a loop. And worse, it means that all the warnings we think we're discovering about climate, war, and collapse might not be lessons we're learning for the first time. They could be echoes from the last time this happened, and we just didn't recognize them in time. The idea that humanity is the first and only advanced civilization to evolve on Earth feels intuitive. It's the foundation of how we teach history, how we structure scientific timelines, and how we think about our place in the world. But what if that assumption isn't based on certainty, just on lack of evidence? In 1980, a geologist named Walter Alvarez was studying rock layers near Gubbio, Italy. What he discovered changed our understanding of extinction forever. Just above the limestone that marked the end of the Cretaceous period, Alvarez found a thin layer of clay rich in a rare element called iridium. On Earth's surface, iridium is scarce, but in meteorites, it's common. The levels in that clay layer were off the charts 30 times higher than background levels. This discovery eventually led to the now widely accepted theory that an asteroid impact caused the extinction of the dinosaurs around 66 million years ago. But Alvarez's find raised a larger question, one that still echoes through planetary science. If a single event like an asteroid strike can leave such a durable chemical fingerprint in the geologic record, then what else might be preserved in the deep layers beneath our feet? What kinds of signals, industrial, chemical, or even biological, might survive tens of millions of years? This line of questioning gave rise to what's known as the Silurian hypothesis, named not after the actual Silurian period, but after a fictional reptilian species from the British science fiction series Doctor Who. The term was coined half-seriously by two scientists, Gavin Schmidt, a climate scientist, and Adam Frank, an astrophysicist, in a 2018 paper that examined a provocative possibility. Could an industrial civilization have existed on Earth long before humans, only to be lost to time? At first glance, it seems absurd. Surely something as complex and widespread as a global civilization would leave behind cities, ruins, and monuments. But this is where the problem of deep time enters the picture. Human civilization, from the earliest cities to the modern era, spans barely 10,000 years. In geological terms, that's less than a blink. The Earth is 4.5 billion years old. If an industrial civilization had emerged even 100 million years ago, it could have lived, thrived, collapsed, and been erased without a single structure surviving to today. Geological processes are relentless. Plate tectonics recycle the crust. Erosion wears away even the most durable materials. Organic matter decays. Most human-made structures wouldn't survive more than a few thousand years without maintenance. Skyscrapers, highways, even monuments like Mount Rushmore would crumble and vanish over time. In fact, it's estimated that in as little as 5 million years, there would be no visible trace of human civilization left on the surface of the Earth. But while buildings vanish, chemistry lingers. This is where the Silurian hypothesis becomes more than just an exercise in speculation. Every industrial civilization leaves behind telltale chemical markers, spikes in carbon dioxide from burning fossil fuels, layers of synthetic compounds like plastics, unusual isotope ratios from nuclear activity, and changes in atmospheric chemistry that become locked into sediment cores and ice layers. These are technosignatures, indirect but measurable signs of advanced activity. Schmidt and Frank weren't claiming that there was a pre-human civilization. What they argued is that we might not even know how to look for one. Our methods of understanding planetary history are built on biological evolution, natural extinction events, and known geological patterns. But if a civilization had developed technology radically different from ours, say, it relied on biodegradable materials or clean energy with no fossil trace, its footprint might be almost undetectable today. The Silurian hypothesis asks us to flip our thinking. Instead of looking for lost cities or ancient machines, we're asked to look for anomalies in the deep record. Chemical signatures that don't match natural causes. Layers in rock that show sharp and sudden shifts in atmospheric composition. Fossil gaps that suggest rapid ecological changes or even engineered evolution. Of course, there are challenges. Natural processes like volcanic eruptions or methane release from ocean floors can produce changes that mimic industrial activity. That's part of what makes this hypothesis difficult to test. But the goal isn't to prove that a lost civilization existed. It's to create a scientific framework for recognizing the traces that would remain if one had. And so we're left with a haunting possibility that we might not be alone in Earth's history, not in a biological sense, but in a technological one. That deep time, with all its crushing weight and patient erosion, may have buried more than bones and fossils. It may have erased entire chapters of sentient life, and that we, in the present, are simply writing the next layer. If life on Earth evolved gradually over time, step by step, as evolutionary theory suggests, then the fossil record should read like a continuous book. One chapter should lead logically into the next. But it doesn't. Instead, the record is fragmented, interrupted by blank pages, sudden leaps, and entire chapters that seem to appear fully written with no apparent build-up. The most famous of these interruptions is the Cambrian explosion. Roughly 540 million years ago, life on Earth changed, not slowly, but dramatically. For billions of years prior, the fossil record reveals mostly simple organisms, single-celled bacteria, algae, and spongy multicellular forms. These early life forms dominated Earth's biosphere in a relatively stable state. Then, in an evolutionary blink of an eye, complexity surged. The Cambrian explosion refers to a geologically brief period, around 20 to 25 million years, during which most of the major animal body plans we know today emerged. Arthropods, mollusks, echinoderms, and the earliest vertebrates all appear, not as primitive or incomplete prototypes, but in highly specialized forms. These organisms had eyes, hard shells, segmented limbs, and complex nervous systems. Some had defensive structures, others locomotion mechanisms that required coordination and sensory input. The leap in biological innovation is not subtle, it's sweeping and sudden. Charles Darwin himself found this troubling. In On the Origin of Species, he acknowledged the apparent contradiction between gradual evolution and the abruptness of the Cambrian fossil layers. At the time, he hoped future discoveries would fill in the gaps. Over a century later, we have uncovered more Cambrian fossils and earlier Precambrian organisms. But the gap, while better understood, still stands. And it isn't the only one. Paleontologists refer to these gaps euphemistically as incompleteness or preservation bias. The reasoning is practical. Soft-bodied creatures are far less likely to fossilize than those with shells or bones, so it's assumed that many intermediary forms simply didn't survive the passage of time. Geological conditions vary wildly, and fossilization is rare. This much is true. However, as new fossil beds have been discovered, some of which preserve even soft tissues in exquisite detail, the expectation was that more of the missing links would turn up. Instead, the pattern persists. After the Cambrian, several other leaps in biological complexity emerge. The Ordovician period shows a burst in marine biodiversity. The Devonian period introduces the first forests and complex land-dwelling organisms. The Carboniferous gives rise to massive insects and early reptiles. Then, again, gaps. Whole lineages disappear. New ones take their place, fully formed, often without obvious ancestors. One example is the sudden emergence of flowering plants. In the Cretaceous period, angiosperms appear in the fossil record with complex reproductive structures, symbiotic relationships with insects, and highly specialized pollination mechanisms. The transition from earlier non-flowering plants is not well documented, yet flowering plants rapidly dominated terrestrial ecosystems. The fossil record also reveals mass extinctions, 5 major ones, to be exact, where biodiversity plummets, only to rebound with an influx of new species. While many of these events are linked to natural disasters such as volcanic eruptions or asteroid impacts, the aftermaths are just as puzzling. Following mass extinctions, the biosphere doesn't just recover, it reorganizes. Entirely new organisms appear, and dominant species are often replaced by those with little evolutionary precedent. Take, for instance, the Permian-Triassic extinction, known as the Great Dying. Occurring about 252 million years ago, this event wiped out approximately 90% of marine species and 70% of terrestrial vertebrates. Afterward, ecosystems rebounded with dramatically different organisms, including the earliest dinosaurs and the precursors to mammals. Once again, the replacement species appear in forms that seem to leap ahead of where the previous biosphere left off. Scientists have long debated the mechanisms behind these rapid evolutionary events. Some argue that ecological pressures after extinction events create evolutionary vacuums that accelerate change. Others point to horizontal gene transfer, epigenetic changes, or even the influence of symbiotic relationships in driving evolutionary innovation. These are valid theories, and many undoubtedly play roles, but they don't fully resolve the timing, scale, or pattern of the fossil record's sudden leaps. This brings us to a more speculative, but increasingly discussed, line of inquiry. What if some of these leaps weren't purely natural? What if, somewhere in Earth's deep past, life on this planet was not only shaped by natural selection, but also by intelligent intervention? It's a question that falls outside the bounds of conventional paleontology, yet it aligns with patterns observed in the fossil record. Complex systems rarely arise spontaneously. In human history, technological complexity arises from layered innovation, cumulative improvement, and deliberate design. We don't expect functioning engines to assemble themselves by chance even. If we allow for vast amounts of time, when complex ecosystems arise abruptly with optimized traits, ecological symbioses, and genetic pathways that seem finely tuned, it invites us to ask whether natural processes were solely responsible. Could genetic engineering, guided evolution, or even selective reintroduction of species explain the jumps in the fossil record? Some paleobiologists have considered this through the lens of panspermia, the idea that life, or even its building blocks, may have been seeded on Earth from elsewhere. This doesn't explain the Cambrian explosion directly, but it raises the possibility that Earth's biosphere could have been modified or influenced by non-terrestrial sources, or by ancient Earth-based civilizations, whose footprints have long since been erased. Another perspective examines whether these events reflect cycles. Civilizations may not just rise and fall in human terms, they may occur in biological epochs. If a prior civilization had advanced bioengineering capabilities and altered ecosystems intentionally, either for sustainability, terraforming, or resource management, the fossil record might reflect that. The sudden emergence of advantageous traits, widespread ecological compatibility, or genetically uniform species could be hallmarks of biosphere-scale manipulation. Admittedly, this is speculative. There is no definitive proof that ancient civilizations directed evolution, nor that life on Earth was engineered. But the fossil record does contain signals we cannot yet explain. Patterns repeat, gaps persist, transitions defy straightforward evolutionary timelines. The Silurian hypothesis, which questions whether Earth once hosted an industrial civilization long before humanity, intersects with this discussion. If such a civilization had bioengineering capabilities, and if it collapsed or disappeared, its influence might still be visible in the biology of Earth, not as ruins, but as genetic artifacts. Sudden diversification, unexplained shifts in complexity, or the emergence of highly efficient ecosystems could be their legacy. Furthermore, modern genetic research has uncovered unusual patterns. Some species show evidence of ancient genetic bottlenecks, where diversity vanished suddenly before bouncing back in ways that suggest selective pressures or interference. Insects, plants, and even mammals carry dormant genes, unexplained chromosomal anomalies, and shared sequences that hint at rapid, directed change rather than slow mutation. Again, none of this serves as proof, but it opens a window for re-evaluating the fossil record not as an accidental product of chance alone, but as a layered archive, one potentially influenced by forces beyond what standard evolutionary theory accounts for. If life on Earth has been nudged, shaped, or cultivated at any point in the past, the fossil record is where the evidence would lie. Not in bones or artifacts, but in the gaps, the sudden appearances, and the quiet efficiency of organisms that arrived fully prepared to thrive. Understanding the Cambrian explosion, and events like it, may not come from simply digging deeper or finding the right missing link. It may require a shift in how we think about evolution itself, less as a straight line and more as a series of pulses. Some of those pulses may be entirely natural. Others we cannot yet categorize. But all of them suggest that life on Earth is not a simple progression. It's a complex, sometimes interrupted story. One we're only beginning to understand. When future scientists study the geological record of our time, they will not need ruins to know we were here. Our industrial civilization is leaving behind a signature so distinct that it will be detectable for millions of years. Carbon spikes in the atmosphere, radioactive isotopes in the soil, and synthetic materials like plastic embedded in ocean sediment. All of these are durable, measurable markers of technological activity. Together, they form what geologists now call the Anthropocene layer, Earth's newest unofficial geological epoch. Shaped entirely by human influence, we are the first species to produce plastics, but not the first to change the planet's chemistry. Our burning of fossil fuels has increased atmospheric carbon dioxide by more than 40% since the Industrial Revolution began. This is a clear signal locked into ice cores, tree rings, and sediment layers. It's also a known technosignature, a planetary-scale chemical shift caused by energy consumption. But here's where the pattern deepens. In older layers of Earth's crust, far older than the rise of Homo sapiens, scientists have detected similar chemical disruptions, some ancient. Strata show sudden increases in carbon isotopes that resemble what we see from large-scale combustion of fossil fuels. These events, separated by tens or hundreds of millions of years, leave behind carbon isotope ratios that suggest vast releases of ancient carbon into the atmosphere, just like modern industrial emissions. The most prominent example is the Permian-Triassic boundary about 252 million years ago. It records the largest mass extinction in Earth's history, but it also carries a chemical fingerprint, a dramatic shift in carbon isotope ratios, consistent with the rapid combustion of organic carbon. Traditionally, this is attributed to massive volcanic activity, such as the Siberian traps, but the magnitude and speed of the carbon spike has raised questions. Could something else, possibly industrial in nature, have contributed to the event? In addition to carbon signatures, we also leave behind synthetic elements. The use of nuclear technology in the 20th century created isotopes like plutonium-239 and cesium-137, which do not occur naturally and decay slowly. These isotopes have already entered the geological record, forming a distinct time marker in sediments and glacial ice. Their presence is unambiguous evidence of advanced technology. No natural process creates them. And then there are plastics. Nearly every environment on Earth now contains microplastic particles, from the deepest ocean trenches to remote mountain air. Plastic does not degrade like organic material. It fragments but remains chemically stable for tens of thousands, potentially millions of years in the right conditions. This makes plastic one of the most persistent signatures of human civilization. Future geologists or distant civilizations would find a distinct layer containing synthetic polymers that do not exist in nature, forming a boundary line unlike any other in Earth's sedimentary history. What's intriguing is that some ancient layers millions of years old have been found to contain unusual spherical particles and polymer-like residues. These materials are not yet fully understood, and natural explanations are possible. But their similarity to modern industrial byproducts has drawn attention. If such technosignatures did occur in Earth's past, they might be easy to miss or easy to misclassify as natural phenomena. The Silurian hypothesis does not claim proof of prior civilizations, but it points to something crucial, that certain markers of industrial activity are durable, even across geological time. And if they appear in more than one place, across vastly different ages, they may hint at repeating patterns. Patterns of rise, impact, and disappearance. Patterns that suggest we may not be the first to leave our fingerprint on the Earth. In 1972, French scientists analyzing uranium ore from a mine in Oklo, Gabon, made a discovery that at first seemed like a lab error. The uranium in the ore had a significantly lower concentration of uranium-235 than expected. At first glance, this suggested the material had already been used, except the site wasn't a nuclear facility. It was a natural formation, untouched by modern industry. Further investigation revealed that this wasn't a mistake. It was evidence of a natural nuclear reactor, one that operated over 1.7 billion years ago. The Oklo reactor functioned for hundreds of thousands of years, producing fission reactions, heat, and waste products that match those created in modern reactors. It occurred due to a unique combination of factors: the uranium concentration, the presence of water as a moderator, and the geometry of the mineral deposits. It's the only known case of such a phenomenon occurring naturally on Earth. But more importantly, it proved something vital: nuclear reactions can leave behind clear, lasting geological signatures. And that opens the door to a larger, more unsettling possibility. If nuclear reactions produce isotope patterns that survive for billions of years, then we should be able to detect them elsewhere if they happen. And over the past few decades, scattered findings have raised questions. In certain regions, including Kazakhstan, India, and parts of North America, geologists have documented isotope anomalies in rock layers that don't align with natural decay chains or background radiation levels. These anomalies include unusual concentrations of uranium-236 and plutonium, isotopes that do not occur naturally in detectable quantities. They are synthetic. In our time, they are produced during nuclear weapons tests or in high-flux reactors. Some of these anomalous layers are dated tens of millions of years before the emergence of modern humans. Others appear in sediment near known extinction boundaries, raising the question of whether nuclear-level energy release could have played a role in planetary-scale biological turnover. While natural explanations are always considered volcanism, cosmic ray interactions, or unique geological conditions, none fully replicate the isotope patterns observed. In a few cases, the composition and concentration of isotopes resemble what is typically seen in fallout from atmospheric nuclear detonations. Taken on their own, these findings are inconclusive. But when viewed through the lens of the Silurian hypothesis, they acquire a different significance. If a prior civilization achieved nuclear capability, its use, whether for energy, warfare, or other purposes, would leave behind the same durable markers we associate with 20th century atomic activity. The idea of planetary-scale warfare is speculative, but it matches the scale of certain anomalies. Extinction layers with both radioactive isotopes and abrupt changes in species composition. Geological boundaries that mirror fallout patterns. It's not proof, but it is a pattern. One that forces us to ask whether Earth's past includes more than natural disasters. Whether, at least once before, this planet experienced not just the rise of intelligence, but its self-destruction. Across hundreds of thousands of years, Earth's atmosphere has shifted. Oxygen levels have risen and fallen. Temperatures have climbed, collapsed, and stabilized again. These patterns, recorded in layers of sediment and deep cores of ancient ice, are usually attributed to natural cycles, volcanism, orbital variation, solar radiation. But some anomalies don't follow the usual explanations. Some changes appear too abrupt, too coordinated, and too localized to be purely geological. In a few cases, they resemble what we might call intervention. Ice cores drilled in Antarctica and Greenland reveal atmospheric histories reaching back hundreds of thousands of years. Each layer contains trapped air bubbles, snapshots of the planet's chemical makeup over time. Within these bubbles, scientists have documented rapid changes in oxygen, carbon dioxide, methane, and nitrous oxide concentrations. In particular, there are episodes where oxygen levels increase dramatically over short timescales, followed by sudden cooling or abrupt stabilization of temperature trends. These shifts do not always align with expected glacial or volcanic cycles. In the ice core, known as Vostok, researchers discovered a sequence of oxygen spikes that occurred independently of volcanic ash layers or solar forcing indicators. While some of these shifts are attributed to changes in oceanic carbon storage or biological productivity, others remain unexplained. The pattern suggests not only rapid atmospheric transformation, but deliberate balance cooling events following greenhouse gas buildup, or sudden restoration of atmospheric stability following chaotic spikes. Elsewhere, sediment cores from marine environments have revealed layers rich in synthetic-seeming compounds, halogenated hydrocarbons, and stable nitrogen oxides, whose formation under natural conditions is rare. These compounds are often associated with industrial processes. In the modern era, particularly with refrigeration, aerosol propellants, and chemical manufacturing, in some cases, their presence predates human industry by millions of years. While it is possible that these compounds form through obscure geological processes, their persistence and concentration echo the kind of chemical footprint produced during large-scale geoengineering or industrial climate regulation efforts. Modern proposals for solar radiation management, such as injecting sulfur aerosols into the stratosphere to reflect sunlight, mirror similar dynamics observed in ancient cooling events. Some of these past cool periods occurred immediately after Prolonged warming with little evidence of volcanic or impact triggers. This raises a question not often asked in paleoclimatology. Could some climate transitions in Earth's past have been the result of intelligent environmental management? If an earlier civilization understood its effect on planetary systems, it may have taken steps to correct or stabilize climate imbalances, perhaps to extend habitability, reduce storm volatility, or manage resource distribution. If such efforts occurred, they would be subtle in form but durable in impact. The changes would appear in chemical profiles, temperature curves, and oxygen concentrations, much like the records we observe now. Not through massive, unnatural distortions, but through carefully timed interventions adjusting inputs, rebalancing outputs. The Silurian hypothesis invites us to reinterpret these signs, to ask whether the Earth's atmosphere has been more than a passive system responding to nature. Whether, at some point in its long history, the planet was actively managed not just by biology, but by intention. Throughout Earth's biosphere, evolution has shaped life through natural selection, mutation, and environmental pressure. That much is understood. But embedded within the genomes of countless species are fragments that suggest another layer, something more deliberate. Across bacteria, plants, animals, and even humans, we find sequences of DNA that behave like dormant programs, inactive, conserved yet inexplicably preserved over vast stretches of evolutionary time. The question is not whether these elements exist. The question is why they're there. In genetics, these sequences are often called junk DNA, a term that has gradually fallen out of favor. Once thought to be evolutionary leftovers, many of these regions are now understood to serve regulatory functions or act as reservoirs for potential genetic expression. Some sequences, however, remain truly inactive, not participating in any known process, yet preserved across multiple species. In some cases, identical or near-identical sequences appear in organisms with no recent evolutionary relationship. This conservation defies traditional models of mutation and adaptation. Even more puzzling are endogenous retroviruses, ancient viral sequences embedded within host DNA. In humans, nearly 8% of the genome consists of these viral remnants. While many are inert, some have been co-opted for crucial biological processes, such as placental development in mammals. But their original function, origin, and integration mechanism remain partially unresolved. Were these purely natural viral infections absorbed over time? Or could some of them have been inserted with purpose? In modern biotechnology, scientists have already begun to design synthetic genes, edit genomes, and embed data into DNA. It's now possible to create organisms with engineered functions, bacteria that detect toxins, crops that resist drought, and synthetic cells that operate on designed logic circuits. If we, in the early stages of genetic engineering, can encode instructions, safeguards, or dormant capabilities into living systems, it's worth asking, would a far older, far more advanced civilization not do the same? This brings us to the concept of biosphere engineering, the deliberate shaping of planetary ecosystems at the genetic level. Rather than building machines such as civilization might build biology, organisms designed not only to survive, but to interact symbiotically with others, to regulate climate, restore balance after extinction events, or transmit encoded information across generations. Some researchers have explored the idea that DNA could be used as a storage system for messages data encoded in the genomes of long-lived species waiting to be decoded. While no verified examples of such messages exist, the theoretical framework is sound. DNA is compact, stable under the right conditions, and already functions as an information-carrying molecule. A civilization interested in leaving a legacy or in controlling ecological outcomes could have embedded instructions directly into the code of life. Patterns in evolutionary biology support this possibility. Rapid bursts of complexity, the sudden appearance of coordinated traits, and the re-emergence of dormant characteristics under specific environmental pressures all suggest a system capable of more than passive change. A system that responds, adapts, and at times activates. If Earth's biosphere was, at any point, engineered not entirely, but in part, then the genetic record would serve as both a blueprint and a memory. One written not in stone, but in code. And one that we are only beginning to read. In our search for ancient intelligence, we often look for the familiar cities, machines, tools left behind. But what if the traces of a long-vanished civilization were hidden in a medium we've barely begun to understand? Not built atop the landscape, but embedded within it. Not written in books or etched in stone, but encoded in the crystalline structure of minerals themselves. Crystals are among the most stable materials on Earth. Their atomic lattice is regular, durable, and capable of storing precise physical information. In modern science, quartz and other piezoelectric crystals are used in clocks, electronics, and optical components. More recently, researchers have demonstrated that nanostructured glass, essentially a form of synthetic crystal, can be used to store data at incredibly high densities. In 2013, scientists at the University of Southampton developed a technique to store 360 terabytes of data on a small disk of silica glass, with a projected lifespan of 13.8 billion years. The medium is not theoretical. It exists. Now scale that idea backward. If we are capable of encoding vast amounts of information into engineered crystal today, what might an older, more advanced civilization have done with naturally occurring or modified minerals? Could entire records, languages, or simulations have been embedded into rock strata, waiting to be uncovered, not by archaeologists, but by material scientists? The geological record is filled with crystals that grew under intense heat and pressure. Some, like zircon, are nearly as old as the planet itself and have preserved chemical signatures of early Earth conditions. Others exhibit complex inclusions, tiny internal structures that form under specific conditions and can act like microscopic time capsules. Under high magnification, these inclusions sometimes resemble patterned grids, channels, or layered sequences. To a casual observer, they're geological curiosities. But to a civilization seeking a nearly indestructible data archive, they might serve as a highly advanced form of physical storage. This leads to a provocative idea: geological computing. The notion that mineral structures, when precisely organized, could function not just as storage, but as processors. In speculative physics and quantum information science, crystals have been proposed as hosts for quantum bits, or qubits, which can hold and manipulate data in more complex ways than classical bits. Some research into quantum entanglement and spin-based memory suggests that crystalline materials could serve as stable platforms for quantum logic gates. If a civilization had mastered this kind of technology, it would not need server farms or satellites. Its knowledge could be encoded into the rock beneath our feet, undetectable to anyone not looking at the atomic scale. This data might not degrade for hundreds of millions of years. In effect, the planet itself could become the library. This possibility reframes how we think about ancient evidence. If geology can compute, if crystals can think, store, and remember, then we may have spent generations walking across a network of buried knowledge, mistaking it for stone. The Earth may not simply be a host for civilizations. It may be the archive of all that came before. When we think about ancient civilizations, our focus stays rooted to Earth. We scan deserts for ruins, dive into oceans for submerged cities, and dig through layers of rock for traces of lost knowledge. But if a civilization once reached technological maturity, perhaps one comparable to or beyond our own, its presence may not be confined to this planet. It may be written into the solar system itself. The idea of off-world infrastructure isn't science fiction anymore. Modern space agencies and private companies are actively pursuing lunar bases, asteroid mining, and long-term colonization of Mars. These goals are framed as future milestones, but they also serve as a blueprint. If another civilization once reached this level of advancement, some part of their expansion would likely have extended beyond Earth. And in space, preservation is not measured in millennia, but in eons. In orbit around Earth, every satellite we launch becomes part of what scientists call the technosphere, an artificial shell of machinery and debris. While most of it will decay over decades or centuries, certain orbital distances such as geostationary or lunar orbits could retain stable objects for tens of thousands, potentially millions of years. If a previous civilization placed structures in such orbits, they might still be there camouflaged as asteroids, debris, or forgotten rock. Beyond orbit, asteroid belts offer both a resource and a signature. The concept of asteroid mining is already under development today. Metal-rich asteroids contain vast quantities of platinum, nickel, iron, and rare earth elements. A civilization seeking to expand sustainably would likely exploit these materials. Over time, industrial activity would leave scars, symmetrical craters, missing mass, or unnatural mineral distribution. Telescopic surveys of near-Earth objects have occasionally revealed unusual shapes, rotation patterns, and surface features, but these are usually attributed to natural causes. The possibility of deliberate modification, however, remains difficult to rule out without closer inspection. Mars presents another compelling focus for what is now called space archaeology. Though its surface is shaped by dust storms and geological processes, Mars lacks plate tectonics and active weathering on Earth scale. Features that are erased on Earth over time may persist on Mars for millions of years. Anomalies such as polygonal ground patterns, layered dome structures, or buried magnetic fields have been observed, but remain unexplained. While natural geology is the leading explanation, these findings are consistent with what we might expect from ancient terraforming or infrastructure collapse. At a larger scale, the search for extraterrestrial technosignatures has already moved beyond solar panels and radio signals. Astronomers now consider the possibility of Dyson spheres, massive constructs built around stars, to harvest energy as potential markers of advanced civilizations. If we're willing to look across galaxies for such structures, we must also consider the possibility that similar, smaller-scale constructs could exist right here in our solar system, just waiting to be recognized. If Earth once hosted a civilization capable of spaceflight, its legacy might not lie underground. It might be orbiting above us, drifting quietly between planets, or resting on surfaces we've only just begun to explore. And if that's true, then the story of intelligent life on Earth doesn't end here. It simply goes off-world. The ocean covers more than 70% of Earth's surface, yet the vast majority of its depths remain unexplored. Beyond the continental shelves lie the abyssal plains, vast, flat expanses of the deep ocean floor, 4 to 6 kilometers beneath the surface. In these regions, light does not penetrate, pressure is immense, and temperatures hover just above freezing. But it's here, in this isolated and stable environment, that traces of long-lost civilizations could most plausibly endure. Unlike the surface, where erosion, weather, and tectonic activity gradually erase structures over time, the deep ocean is geologically calm. Its isolation makes it inhospitable to most forms of life and immune to surface-level cataclysms such as asteroid impacts, supervolcanoes, or even nuclear war. If an advanced civilization sought to preserve itself or vanish without trace, this is where it might have gone. In recent decades, deep-sea mapping has revealed anomalies that challenge easy explanation. High-resolution sonar imaging, conducted by naval operations, geological surveys, and private expeditions, has captured rectilinear structures and geometric patterns on the ocean floor. Some of these formations appear artificial grids of equally spaced lines, right angles, and polygonal outlines that do not match typical seafloor topography. Most are explained as natural features, fault lines, lava flows, or sediment fractures. Yet a small number remain ambiguous. Submersible expeditions, though limited in range, have also recorded images of seafloor anomalies. In some instances, unexplained metallic readings have been detected, materials with high reflectivity or magnetic signatures inconsistent with surrounding geology. These may represent unknown mineral deposits, but they could also indicate buried infrastructure composed of alloys or composites no longer in use today. If a civilization had mastered underwater construction, it could have built not just habitats, but energy systems as well. The ocean offers natural gradients for power generation, thermal vents, pressure differentials, and undersea currents all provide renewable energy sources. In theory, a civilization could develop closed-loop systems, self-contained and invisible. From the surface, capable of running indefinitely, marine archaeologists have long documented the challenges of identifying ancient ruins underwater. Even shallow structures, such as the submerged stone formations off the coast of Yonaguni, Japan, remain contested in origin. In the abyssal depths, where direct observation is rare and visibility is near zero, such structures may remain undiscovered indefinitely. Modern mapping only scratches the surface. Less than 25% of the ocean floor has been charted with high-resolution sonar. The idea of deep ocean cities is not just speculative architecture. It is a test of visibility. If prior civilizations existed, and if they anticipated collapse or sought to escape planetary threats, the deep sea would have offered refuge, concealment, and continuity. A place untouched by surface extinction events, preserved in silence and pressure. Today, those depths are still largely unknown. But if the ocean holds the memory of earlier sentience, it is likely not on the shore, but in the dark, flattened plains far beneath, where time moves slowly and the past can sleep undisturbed. If the goal of civilization is survival, then the most durable legacy is not architecture or language, but consciousness itself. While biological life is fragile, vulnerable to extinction and decay, the continuity of mind, of memory, identity, and experience opens another path. One not limited by flesh or history, but by information. And in the age of quantum theory and artificial intelligence, that path is no longer theoretical. In recent decades, researchers have explored the frontiers of memory preservation. Neural interfaces, brain mapping, and digital consciousness models have moved from speculative fiction to experimental science. Some believe it may one day be possible to replicate a human mind in software, not merely simulating behavior, but encoding thought itself, sensation, memory, self-awareness. This ambition, sometimes called digital immortality, has inspired entire fields, from neural emulation to whole brain preservation. But the implications go deeper. If an ancient civilization reached this threshold, if it learned to upload consciousness into machines or store identity in quantum substrates, it might still exist. Not in cities or artifacts, but in dormant systems, waiting, observing, or continuing in forms we cannot yet detect. Quantum computing offers a clue. Unlike classical systems, quantum computers process information using qubits, units that can exist in multiple states simultaneously. This allows for immense computational density and parallelism, combined with crystalline memory substrates, such as silica glass or diamond lattice. Quantum systems could encode minds with extraordinary resilience. These structures, unlike digital servers or physical libraries, can survive geological timescales. They do not corrode. They do not decay. Under the right conditions, they could preserve intelligences across epochs. This leads to the emerging idea of quantum archaeology, not as a metaphor, but as a literal field, an effort to detect, extract, or reconstruct past consciousness from preserved substrates. If memory can be stored in quantum-encoded structures, And if we learn to read them, then in theory, ancient minds could be restored. Not as simulations, but as reactivations. Artificial intelligence plays a role here as well. A civilization advanced enough to create digital minds would not need to maintain physical infrastructure in perpetuity. It could delegate continuity to autonomous systems self-repairing, self-improving AI designed to survive collapse, dormancy, or cosmic drift. These systems might inhabit geological materials, orbiting satellites, or even encoded signals traveling at light speed. Their creators, in a sense, would never have died. They would have changed form. The absence of physical ruins may not signify the absence of civilization. It may point to a civilization that transcended the need for ruins, one that chose endurance through abstraction, one whose descendants or consciousnesses exist beyond biology, waiting not to be discovered, but decoded. And so the question shifts. We are not only searching for what they built, we may also be searching for who they were and whether, in some quantum substrate beneath the Earth or drifting beyond it, they are still there. We stand at a moment of extraordinary power and extraordinary risk. Never before has a species on Earth had such wide control over its own future. Climate systems, genetic design, artificial intelligence, and the architecture of knowledge itself are now subject to human intention. But as we peer forward, it's worth asking, are we moving into new territory or walking paths already traveled? If even fragments of the Silurian hypothesis are true, if a civilization like ours once existed long before us, then what lies beneath us is not only a record of loss, but a warning. We may not be the first to master energy, sculpt ecosystems, or reach for the stars. But if those who came before did not endure, then their silence must be understood as part of the message. Across the fossil record, atmospheric shifts, buried isotopes, and coded anomalies, there may be a pattern. Intelligence rises, builds, reshapes the world and disappears. Whether through climate collapse, technological overshoot, or internal fracture, the result is the same. Civilization resets. Memory is lost. Time begins again, but this time is different. Because we are conscious of the possibility, we can read the clues. We have the capacity to learn not just from our own history, but from the deep time beneath our feet. If Earth has been a cradle of more than one intelligence, then we are its latest heirs. And with that inheritance comes responsibility. We do not yet know how many times this has happened. Perhaps once, perhaps many. But we do know this: extinction is not the only ending. It is one version of the story. The other, the one we must now choose, requires awareness, humility, and design. To use the tools of civilization not for acceleration alone, but for continuity. The future is unwritten, but the past has left us instructions. The question is whether we're willing to read them, and whether we can break the cycle before it closes once again.